Hi everybody, it's me, Dr. V, and it's a good day to do some chemistry. In this webcast, I'd like to talk about calculations for doing redox titrations. These are an important skill and something that AP chemistry students need to be able to do. Now, really what we're doing is an aspect of solution stoichiometry. So I'm going to go through the process of titrations a little bit and really focus on math of what we need to do to solve these problems, and then go through a redox titration problem with you. Here's the typical setup. You have a burette with a solution. We call the solution in the burette the titrant. And we have an analyte, which is the substance in the flask below the burette. And then we can open and close the stopcock on the burette. If we measure the initial and final volume of the liquid in the burette, we can calculate what volume of titrant that was used to get the color of the analyte to change color, which we call the endpoint. This is volumetric analysis, right? It's all about measuring volumes to figure something out. When you think about your setup for a redox titration, or really any titration, we know 3 out of the 4. The molarity of the titrant, the volume of the titrant, the molarity of the analyte, and the volume of the analyte. Whatever piece we don't know, that's what we're solving for. We're going to solve for that missing quantity. There are a lot of uses for titration in general, right? The most important one for us is that we can use it to calculate the concentration of an aqueous solution. Another variation for redox titrations is we might find the percent by mass of the analyte in that original sample if we had, say, measured the mass of that analyte before we dissolved it. Let's think about our strategy for solving these kinds of problems. They are, at their heart, stoichiometry problems, and that means you need to start with a balanced equation, because the balanced equation gives you the mole-to-mole ratios that you need to solve the problem. The other thing you want to remember is that at the equivalence point, the moles of the titrant and the moles of the analyte will be in whatever that stoichiometric ratio is from that balanced equation. We're going to have just enough titrant to completely react with all of the analyte. So thinking about these problems, we can use the volume and molarity of the titrant to find the moles of the titrant, for example, and then we can use our mole ratio to then calculate the moles of the analyte. And then, depending on what the question is, in this problem, we're going to use the molarity formula to calculate the molarity of that analyte. Again, we can do other variations on it, but this is the big picture. It's time to do a problem, right? That's what we're here to do. The amount of iron 2 ions in a solution can be determined by titration with a solution containing a known concentration of permanganate ion in the presence of excess acid, as shown in the equation above. Here's the equation. A student carries out this titration using 39.25 mils of iron 2 chloride solution and uses 27.82 milliliters of 0.15 molar potassium permanganate to reach the endpoint when the solution turns pale pink. What is the concentration of the iron 2 ions in the solution? There's a lot going on here, right? If you're wondering where the potassium ions went and where the chloride ions went, they're spectator ions. So I've just got the net ionic equation here. Now we know that we have the molarity of the permanganate solution, and we have the volume of the permanganate solution. We know moles over volume gives molarity. We can rearrange that to solve for the moles of permanganate. The molarity of the permanganate times the volume of the permanganate. Well, we know the volume that was used of the permanganate is 27.82 milliliters. We know the molarity of the permanganate solution was 0.15 molar. So we can substitute that in. 0.15 molar times 0.02782 liters will give us 4.17 times 10 to the minus third moles. Now, I do want to point out, I really only know this to 2 sig-figs, but I'm not going to round for that yet. From the balanced equation, I see that 5 moles of iron 2 ion react with every mole of permanganate that's added. And so I'm going to take my 4.17 times 10 to the minus third moles of permanganate and multiply it by 5, because that will give me moles of iron 2, which is 2.09 times 10 to the minus 2 moles. Again, I only know this to 2 sig-figs. No, I haven't rounded it yet. Yes, I will do that soon. Now, the molarity of the iron 2 ions in the original solution is determined by the moles of iron 2 ions divided by the volume of the iron 2 ions. And we know all of this now. We just calculated the moles of iron 2 ion, and we knew the volume of that iron 2 chloride solution. So we can substitute that all in. 2.09 10 to the minus 2 moles of iron 2 divided by 0.03925 liters, and I get an answer of 0.53 molar iron 2 ions. And that makes sense, and I did report my final answer to 2 sig-figs like I said I would. In terms of wrapping this up, things to keep in mind: make sure you've got that balanced equation. Make sure you've got the right mole-to-mole ratio. Without it, you don't have a chance. Sorry. Read the question carefully. Make sure you have listed out what you know what you're solving for. And when in doubt, with any stoichiometry problem, if you're not sure what to do, solve for moles. If you know the molarity and volume of something, you can find the moles of that. It will never hurt you. It will never be a bad idea to find moles. It's also really important to make sure you show enough work to support your answer. Don't just have answers coming out of nowhere. You need to show how you got there. If you like the video, leave a comment and subscribe to my channel so you get all my latest updates. Have a great day and keep studying chemistry.